Hello everyone, thank you for joining me today. My presentation is Proprioception and Tail Control Enable Extreme Terrain Traversal by Quadruped Robots. Let's image a scenario where a legged robot is trying to navigate extreme terrain. Sudden changes in terrain elevation invalidate their contact, resulting in failure. Interestingly, animals can traverse these terrains without difficulty. We identified two key reasons they are able to: perception and contact robust dynamics. Robots can also use perception to recognize and respond to changes in terrain. The stereoceptive approach is to integrate commercial external sensors such as cameras or LiDAR. However, these methods might be unreliable in extreme environments due to occlusion or lightning conditions. In contrast, proprioception from contact sensors or transparent actuation offers a more complex but robust technique for detecting unexpected changes in terrain elevation. Another way to overcome extreme terrain is to incorporate contact-robust dynamics into the system. This allows the robot to maintain its actuation when missing contact. Leg control can be enhanced with passive stabilization techniques such as wing leg retraction. However, this is limited to small elevation changes. Contact-independent actuators such as tails and flywheels can effectively stabilize the robot during contact loss. However, they require additional coordination and control. In this work, we combined two ideas. We introduced a proprioception-based gait planner that dynamically updates leg planning and control in real time. Additionally, we added a two-dove tail, controlled by a nonlinear NPC, to balance the robot in coordination with the legs. We first extend the clock-based nominal stance swing biphasic contact schedule to a finite state machine by dividing the swing to stance switch into touchdown and reposition, using proprioceptive information including contact force and leg extension as additional conditions. With the finite state machine, we can perform gait planning to adjust the contact schedule to adapt to terrain changes. Proprioception also involves terrain estimation, filtering the discrete foothold histories into surfaces to aid in planning. Here, we show the robot traverses unknown roof terrain and generates estimations without prior knowledge. After the walk, the final estimate accurately captures the peaks and basins of the terrain, providing valuable information for planning. We test the proprioception-based gait planner by simulating a quadruped walking over unforeseen elevation changes. In the video, the robot successfully identifies the contact deviation when stepping off the cliff and responds by replanning its gait to ensure a safe landing. In multiple trials at different cliff heights, the proprioception-based gait planner can robustly walk the robot over ledges up to 1.5 times total leg length with over 95% success. Secondly, we add a two-dove tail on top of the robot using serial roll and pitch actuators. The tail is designed to be long and light in order to provide high enough torque without affecting the robot dynamics too much. For control modeling, the robot is reduced to a single ridge body with a point mass tail. Besides, we also implement sequential distributed nonlinear NPC for the tail robot. It decouples the leg and tail controls but allows them to communicate with each other. This decoupling improves efficiency and compatibility with existing leg controllers. Furthermore, in the efficiency comparison, the sequential distributed NPC reacts much faster than the centralized NPC, especially with long horizons. In addition, compared to the feedback controller, the nonlinear NPC can exploit nonlinear dynamics to return the tail while preserving positive work to increase effectiveness. Finally, we evaluate the further performance gains brought by tails when the robot is initialized with a non-ideal pose. The video shows the tail complements the legs by rejecting the angular IROS and providing a more kinematically feasible landing. The nonlinear NPC loops the tail twice and returns it using the nonlinear dynamics without canceling the positive work. Batch simulation results show that the tail can effectively reduce the maximum angular error and maintain robustness even with a poor initial pose. Overall, we propose a method that combines proprioception that online updates planning and tail that complements unactuated legs to improve extreme terrain traversal capabilities of quadruped robots. We demonstrate on a simulated quadruped robot that can robustly traverse cliffs with high variations of up to 1.5 times the leg length in a tilted initial state. Future work includes performing hardware deployments, considering more types of extreme terrain, and improving the tail design. Thank you.